temperature is a measure of the average kinetic energy within an individual sample. Okay? So if I take a sample that has 100 energy units, let's just say energy for the moment, a single sample that just has 100 energies, what would my temperature reading be? Well, my temperature reading would correlate to 100 energy readings. What if I took a new sample, and that new sample had 2 pieces in it? One was 0. Let's try that math again. One was 50. One was 150. What's my new temperature reading? It's still the same temperature reading as our first sample, okay? Because it's looking at the average within that sample. Okay, that's all you end up seeing. So we can have a larger sample with more and more particles in it, but all we're going to end up seeing is the average result, okay, which is an important distinction to make, particularly when we talk about heat in just a little bit. Okay. When we're looking at our temperature scale, we have 3 different ways to monitor it. Okay, or 3 different unit systems. Just like we had with every other unit system, we end up with multiple different types. We've got the Fahrenheit scale, which is our English system, or really it's kind of just become the American system. We have the Celsius scale, which is the most commonly used, and then we also have the Kelvin scale, which is primarily used in science, and it's very rarely used anywhere else. That said, Celsius does pop up in science as well, but for the most part we try and center on the Kelvin scale. Okay. So if we've got 3 different scales, what does that mean? You need to be able to convert between them, because maybe they represent different things. So let's take a look at Fahrenheit. Let's take the easiest system we can look at. Let's take a look at water. What is water's, I don't know what I said on the next slide, is it freezing? Do I start with freezing? Yeah. What's the freezing point on the Fahrenheit scale? 32 degrees. 32 degrees Fahrenheit. What a weird number that is. What's its boiling point? 212. It's actually interesting. Most people seem to get those messed up. As much as we push the Fahrenheit scale for everything we deal with, the freezing and boiling points most people seem to forget. Okay. How about Celsius? We're looking at 0 for our freezing point and 100 degrees Celsius for our boiling point. And then our Kelvin scale, (273 Kelvin), and it boils at 373 Kelvin. So just looking at those numbers, you can real quickly come up with those conversions in your head, right? How do you convert between Fahrenheit and Celsius? That's not super straightforward. How about Fahrenheit and Kelvin? Well, that one's a straightforward calculation, right? Okay. Celsius and Kelvin? The Celsius and Kelvin one should look really straightforward. What's the difference between our freezing points? 273, boiling point? 273. Okay, so our conversion on our Celsius is relatively straightforward, or Celsius to Kelvin. But our Fahrenheit to Celsius and our Fahrenheit to Kelvin, not straightforward at all. That's not particularly fun. So we want to come up with some system that allows us to convert. You can go through and look at a variety of different conversions. Your Celsius to Fahrenheit, assuming I didn't make another typo on this slide, will always be provided. So if you take a look at your exam, the very front, what does it have at the bottom of it? Celsius to Fahrenheit. It was already on that last exam. So you have that conversion. The equation for Fahrenheit to Celsius, okay, I will expect you to derive that one. Okay, and by derive, you can just plug and chug into your first one and solve. Okay? You're being expected to do some algebra to go through and do that solving. If you have problems with that, feel free to talk to me and we'll work through it together and make sure you're square on the algebra, because you need that skill to process. Okay? The last one, to convert Celsius to Kelvin, all you have to do is add 273. You'll notice I did not write 273, I wrote 273.15. Any ideas why? One of the random numbers that I happen to have memorized is the conversion to 5 significant digits from Celsius to Kelvin. Why? I have no idea, but it's there. Okay? You're responsible for 273. That's the only 3 digits you need to know. So a couple hands. I'll come back to you, Mahalat. No, that's what you're going to ask about, Mahalat?
What does it mean when you say that Kelvin is the absolute value?
So it is the absolute temperature scale. What happens to Fahrenheit when we cool it down? We're at 32 degrees Celsius. What happens as we continue to cool?
Goes below 0.
It'll go below 0. How do we represent that with our numbers?
Negative.
Negative. What happens to Celsius?
Negative.
Negative. Both of those temperature scales introduce a negative sign. That negative sign would then need to translate into all of our calculations. So just like we ran into with exponents and negative exponents, it starts to become a confusing mess. So scientists look at this and said, that is an awful system. I don't want to deal with the minus sign. Kelvin. What happens when we go colder in Kelvin? You approach 0. You can never achieve 0 degrees Kelvin. Okay? So that's the issue with our Kelvin scale, is it's an absolute scale. All temperature readings on the Kelvin scale are positive, which is nice when we go through to do calculations because we don't have to worry about sign changes. Okay?
It's kind of weird. It really could never go back to
Leave it to a physicist to mess with it. There was allegedly a experiment that was designed that achieved negative kelvins.
Really?
Yeah. And it's more like a theoretical repercussion of their experiment in thermodynamics. They didn't actually get to negative temperatures. Just the way the system acted, the only way it could act in that way is if it had negative temperatures. Okay. So kind of a bizarre system to look at. If you're interested in that, talk to me in like 5 or 6 years when you've taken a whole lot more physics classes. And then you can probably explain it to me. Okay. So our Kelvin scale, absolute 0. We always keep it positive. Okay. It's the optimist, right? Because optimists are positive. Yeah. Body temperature, 98.6 degrees Fahrenheit. What is body temperature in degrees Celsius and in Kelvin? Go ahead and take a swing at that. If you got questions on the conversion, raise your hand. I'll come to you. One thing that is incredibly helpful to go through and do, and this is something you should be thinking about as you process through these questions, is coming up with some way to approximate. Our Fahrenheit is 98.6. Okay, so it's somewhere in between our boiling point, or our freezing point, and our boiling point for water. So when we're at 98.6, what number should I be getting for Celsius? It should be somewhere between 0 and 100. If it's not between that, something's wrong. Okay? Keep it as simple as that. That just means something is wrong. Same deal with our Kelvin. Why is this kind of simple approximation important? Well, based on grading the physical measurement lab that we did 2 weeks ago, some people did not go through and evaluate between those numbers. It's very easy to swap that 5/9 with 9/5, and now your number all of a sudden becomes significantly different, and you get a really weird answer. Okay? You should be able to look at it and say, that is a weird answer. I did something wrong. Let me do it again. If you get the same answer again, well then, unfortunately, okay, whatever you're doing is consistent and theoretically consistently wrong. You just kind of have to accept it and move on. Okay? So when you go through and do this, you should find that the degrees Celsius conversion gets you to 37. Does it come out as 37 exact?
Yeah, exactly.
Oh, cool. If we reported this, what would we say our answer was? Which would be sig figs.
0.0.
We need the 0.0. This definitely gets a little bit weird because we got the 9/5 and the 32 floating through there.
Right.
Assume those are exact.
Okay.
Okay. So if we start with 3 sig figs in our Kelvin or our Fahrenheit, our Celsius should come out as 3 sig figs. Okay. So we should specify that as 37.0. It's enough of a gray area that you won't see me explicitly test on that. I will probably circle answers and make it look like I'm taking off points, but not actually take off points. Okay. Kelvin, What do we have to do to get our Kelvin? Add the 273 to our 37, and we get 310. Okay, this is where we can run into an interesting dilemma. Whoops. If you write 0.15, what did you do?
You added significant digits.
We had 37.0, and we had 273.15. You add that up, you definitely get that number. How many sig figs are you allowed to carry through?
3. What do you round that?
Not 3. What's that? It is sort of still sig figs, but what happens is our rule changes. Remember, when we do multiplication and division, it's the number of sig figs. Addition and subtraction, the least precise place. Which is the least precise place between those two numbers? The tenths position, which would mean our answer needs to be, it's to the least precise place, not the number of sig figs, the least precise place. The least precise place in this case is the tenths. That would be 310.2.
So do you want us to use 273.15 or 273?
There's our good question. Which one are you responsible for? 273.15 or 273? 273, not 273.15. If you happen to remember it, hopefully you don't see this kind of delineation happening on your answer choices. Again, because I'm aware of this issue, you wouldn't see it. If you now add these two numbers, which is your least precise place? Sorry, I got to clean that. Our ones place, which our answer becomes 310 Kelvin. So depending on what you are using to do your conversion, you're going to end up with different significant digits. Be careful with what you're using. 273 is what you are responsible for knowing. Okay? So anytime you go through and do a calculation, that's what you should use. Again, I'm aware of this issue with using our conversions. They're either 273 or 273.15, which means if it shows up on a test, you won't get the three answers, 310.15, 310.2, and 310. I would never do that. Okay? The only way I could possibly do that is I say report your answer to 4 sig figs, in which case your answer becomes 310.2.
Unless you didn't do the 0.15.
And then you'd say 310.0. Either way, you still have 4 sig figs.
If it's an absolute scale, why would that even matter?
All the absolute scale means is that we don't use the degrees. That's all you need to be concerned about. Okay? So to do our conversion, it's 273.15. The 0.15 does translate into our conversion. That is important for our conversion, depending on the accuracy of what you're trying to aim for. Okay? That has nothing to do with the absolute scale.
Okay.
Questions? How many more tests are you going to have to worry about sig figs for?
The rest of eternity.
Arguably not. If you're concerned about this first test and you're saying, well, man, every question was sig figs. Not true. Okay? So there are some shortcuts on figuring out if you need to worry about sig figs or not. That's what you should talk to me about after class if you would like to see those shortcuts. Most typically, I don't ask sig fig questions. Okay? The first exam absolutely showed up. The rest of the exams, you probably won't see it. Okay? Our heat concept. Temperature measures the average energy. Heat is a measure of the total energy. Okay? Which seems kind of odd that we would differentiate between these two. But remember the system that we looked at, that we looked at before. We had two systems. In one system, I said we had one particle and it had an energy of 100 energy units. In the other system, we said we had two particles, one at 50 energy units and the other one at 150 energy units. Our temperature for both of these is 100. What is our heat? 100 and 200. So heat measures all of the energy within the system, okay? Not just the average energy. This becomes important because if I take a 100-degree cup of coffee and pour that on myself versus a 100-degree eyedropper of coffee and pour that on myself, the eyedropper is going to hurt me less. Why? What's less? The heat is less. The temperature is identical, but the heat is less. There's less particles to transfer energy into my skin, so it burns me less.
Did we miss that question?
I don't know. You'd have to take a look at the exam. That question showed up on your exam.
Yes.
Okay? Heat doesn't use the energy units that I've been picking, where we just pick some arbitrary E for energy unit. We end up using a couple other energy terms. Those are joules and calories, ultimately coming from two different sources. One guy, pretty sure his name was Joule. Calorie, anybody know the source of calorie? I don't think his name was calorie. Right. The science is old. You have multiple scientists working on the same concept in different locations. Very rarely did they ever talk to each other until they discovered something. So Joule went through, came up with an energy term, said, haha, I'm going to name it after myself because I'm awesome. Somebody else came through and said, ha, I found an energy term. I'm going to call it calories. They shared their research and they went, oh crap, we're talking about the same thing. Well, you should change your energy term. Right? The other guy said, no, you need to change it. They ended up fighting a whole bunch. We go into world wars, and we now have to worry about both of them. Okay? In future classes, you are responsible for the conversion between joules and calories. I don't care. So you don't need to worry about that conversion for this class. Okay? Just realize that joules and calories are both a term for energy, a measure for energy. We will see joules show up more frequently as an energy unit. That said, the very next thing we look at is specific heat, which uses calories most typically, but we also have a conversion here where we can relate it to joules. What is our conversion between calories and joules? 1 calorie equals 4.186 joules. How'd you do that? There's a bunch of grams and degrees Celsius in there. Almost don't look at it, not quite.
Well, the bottom are the same. So
The bottoms are the same, and you can multiply across and cancel those units. Right? Specific heat is what we're actually looking at within this. Right? That thing implies a certain piece of information about a particular property. Right? So if we look at any kind of compound or element, we can refer to its specific heat. Hey, I said it. Okay? It is the amount of energy necessary to put into our sample, so that's our calorie, our energy term up top, to raise the sample by 1 degree Celsius. Right? In particular, 1 gram of that sample by 1 degree Celsius. Okay? That's what the specific heat is referencing. Okay? The larger the specific heat, oh, look at out that door. The larger the specific heat, nobody turned. Thanks for pretending to agree with me here. The larger the specific heat, what? What does that mean? Okay, yeah. I have to put more energy in to get the sample to rise by 1 degree Celsius. Okay? What about the smaller the specific heat? The less energy I have to put in. This indirectly references something we've already vaguely talked about. If I stick a match up to, say, a pot, and I touch the inside of the pot, what happens? Pot should get hot pretty quickly. But what if I take, say, an UV glove? You all use, or at least heard of UV gloves? No? Really? No? We need something else.
stick it on your hand and
Yeah, we could do your hand. If we used your hand instead of the pot and stuck a match at the bottom and then tried to touch the top, are we going to feel the heat at the top of your hand? Okay. Eventually, but it's going to take a whole lot longer. Okay, we're going to have to put more heat in the bottom of your hand to be able to detect that temperature change at the top. What does that mean about the specific heat of our pot versus our hand?
Has a lower specific heat.
Which has the lower specific heat?
Metal.
The metal, or our pot, has the lower specific heat because it requires very little energy to go into it before it translates across to the other side. Okay? What is our pot made out of? Metal. What is your hand made out of? Carbon, which is a nonmetal. What we're actually specifying here is the ability to conduct heat. Metals conduct heat very well, which means what happens to their specific heat? It's very low. Nonmetals, we remember all the way back to our beginning, don't conduct heat very well, which means they have a very high specific heat. So I can completely dodge the bullet of doing any kind of conversion calculations here, because what I can do instead is write a very quick exam question that now tests across multiple subjects. Specific heat understanding, metals and nonmetals, and the properties of our metals and nonmetals. How did I make this question even more complicated?
You wrote 10 and put S in both.
How did I make the question that's on the board more complicated? What about the answers? Some of them are symbols, some of them are the words, the names. Meaning, not only am I testing those four things, I'm adding a fifth, and that fifth is, did you do what I asked and actually memorize the name of our common elements? So, to answer this question, there's a couple ways to approach it. First way to approach, the material. Largest specific heat, what does that mean? It is harder to heat up. Which material is harder to heat up? Okay. I want it more general than that. Our nonmetals. Where are nonmetals found? In our upper right-hand corner. Which of these show up in the upper right-hand corner? Well, where's calcium? The left side, so that doesn't work. I can eliminate that. Chromium? Somewhere in the middle, but not our upper right. Okay, and we got that staircase to help us out. Ooh, copper. First thing I have to do, we can kind of cheat and just call it a metal. Well, let's use the periodic table. We'd have to know the symbol for copper. Our symbol for copper is Cu, which happens to show up on our periodic table. Metal range, Pb, which is lead, which shows up in the metal range. Carbon, a C, which is our nonmetal. What do we have? Our answer. You want the other trick? The one that requires absolutely zero understanding of the material? Not quite. You still need to know the difference between metals and nonmetals. Calcium, metal, chromium, metal, copper, lead, carbon, nonmetal. You all watch Sesame Street when you're a little kid? Which one of these things is not like the other? There's our answer. Okay? So take advantage. If you've got no idea what's going on within the question, look at your answer choices and do the best you can to eliminate things. Okay? Questions on that? Okay. Last slide is a nice fun little curveball. We're actually going to turn it into a quiz. Do you have to have heard of or used? Okay, so chapter 4 is all about the models of the atom. So we've got Dalton's atomic theory, which we put up there real quickly on that last section. What we were concerned about is what Dalton went through and did. So way long time ago, he started looking around at these different things in the early 1800s. Okay. Looked at the world around him, and he was able to piece together that there are certain indivisible elements. And you can then combine those elements to make compounds. And there were strict rules that came across or came through when you went through and did that. He wrote down those rules and then applied them. Okay, so we came up with a hypothesis where all of those are his individual hypotheses and then applied those hypotheses things to experiment to make sure everything worked. Okay? So his general hypotheses. An element is composed of tiny, indivisible, indestructible particles called atoms. Is it true? Nope. But it's pretty close. Okay? All atoms of an element are identical and have the same properties. Is it true? Nope, but it's pretty close. 3, atoms of different elements combine to form compounds. Yeah, you got one right. Good job. Okay. Remember, early 1800s. Okay. How many of you thought about and did all of this before you came into the class or took any class on chemistry? That's pretty impressive because that's what he was doing, and he didn't have any of the technology that you do. Okay. Compounds contain atoms in small whole number ratios. It's true. All the way through, that one's true. So when we take compounds, we're combining the different atoms to make those compounds. And number 5, atoms can combine in more than one ratio to form different compounds. Also true. For instance, if I take hydrogen and oxygen, I can combine them to make water. Cool, H2O. I could also take hydrogen and oxygen and combine them to make hydroxide. Hydroxide is OH minus and not water, good answer. An incredibly strong base, not particularly pleasant to drink. I could also combine hydrogen and oxygen to make
Heavy water. Hydrogen peroxide.
what was that?
Heavy water is in the book, something like that. So,
Heavy? Oh, we'll talk about heavy water too. We can combine it to make H2O2, also known as
hydrogen peroxide.
hydrogen peroxide. There's that horrible chemistry joke that you're more than we can just reiterate it. Guy walks into a bar and orders water. His friend walks up and says, "I'll have one of those too." What does he get? H2O2, and he dies. Peroxide, not pleasant to drink. I pretty much ruined that joke, by the way. So, not that it was ever that good to begin with. Thompson came along in the late 1800s. Okay? And Thompson is responsible for coming up with electrons and protons, or at least the theory behind these. Okay? And he was able to determine the relative charge of those particles. One was negative and one was positive. Okay? So where this separates from Dalton's theory is Dalton said that we have indivisible elements. Well, Thompson came along and proved that each of those elements could be decomposed into negative charges and positive charges. So our first rule, what was it, the first rule? Yeah, our first rule in Dalton was that we can't break them apart. We can break them apart into these negative and positive particles. And why I particularly find this fascinating is this all hinges on a single discovery. Anybody know what that discovery was? It's a bit silly. The existence of an electron came about because of the discovery of a vacuum. Without the existence of a vacuum, we cannot discover electrons. Okay, why? Electrons are charged. Not really a vacuum cleaner, but just a vacuum in general. Okay. Electrons are charged. Anything that is charged is very high in energy. For instance, your little brother or sister may have told you to stick a fork in the electrical outlet because they thought it would be funny. Okay, why is that a bad thing? What's coming out of the electrical outlet? Charge. Okay, charge is inherently unstable. If we do not have a vacuum, and I now try and make an electron beam, that electron beam hits air, molecules within air that cancels the electron's existence. So if we have a lot of air around us when we're trying to make that electron beam, we can't see the lifetime of an electron because it immediately disintegrates or it immediately reacts with the air around it and we no longer can see it. A vacuum becomes important because with a vacuum, what can I do to the air? Get rid of it, which means there's now no particles in the way so that when I make my electron beam, nothing encounters the electrons and I can actually see them exist. That seeing them exist is a cathode ray tube, also known as those old school televisions, the CRTs, the big boxes. That's how we discovered electrons, through TV. Not quite, but close enough. We're done, sorry. Thank you for your patience.